So I want to walk through just one more. I want to do a higher order differential equation just to kind of show you how all of this works with higher order. The process is the same. You still have to figure out what the associated homogeneous differential equation solution looks like. That's called the complementary solution. And then we figure out what a good guess is, an educated guess, for the particular solution. Make sure there's no repeats between that particular solution and the complementary solution. And then we go through and we find successive derivatives. Substitute in, compare coefficients to create that system. And then we've got our particular solution. So the general solution is the sum of the complementary plus the particular. So if we look at this example, we have a third order differential equation. It's y triple prime plus y double prime equals e to the x times cosine of x. So let's go through and start by finding the solution to the complementary differential equation. So our complementary differential equation is y triple prime plus y double prime is equal to 0. Our auxiliary equation would be m cubed plus m squared is equal to 0. We could factor out an m squared, which leaves us with an m plus 1. So we know we have 3 zeros or 3 roots. We have m is equal to 0. Now that does have a multiplicity of 2. That will play into what our complementary solution looks like. And then we have m is equal to negative 1, which has a multiplicity of 1. So then our complementary solution would be c1 e to the 0x plus c2 times x e to the 0x. That's because of the multiplicity of 2 and the fact that these have to be linearly independent, which is why we multiply through with an x there. Plus c3 e to the negative x. Now I'm just going to simplify this a little bit. We know e to the x is the same thing as 1, so this is really c1 plus c2x plus c3 e to the negative x. So now let's come up with our educated guess for our particular solution. So if we examine what's going on the right-hand side, that non-homogeneous piece there, we have an exponential times cosine, which means our particular solution has to be in the form of an exponential times our trig. So we could say b sine of x plus c cosine of x. Now we know when we multiply through here, we're going to have a times b, which is just another constant. And then same thing here, a times c is just another constant, so I'm just going to call it e. So there's our particular. Now we're asking, do we have any duplications between here and here? And we see that we don't have any kind of duplications. So we are good to go to our next step. All because we have linear independence between each of those functions. So now we need to look at the substitution, but before we do that, we've got to find derivatives. So if we look at first derivative, we're going to have to apply product rule. So it's first one, derivative of the second, plus second one, derivative of the first. Apply product here. So it's going to be first one, derivative of the second, but the derivative of the cosine is the negative sign, plus the second, derivative of the first. To find second derivative, we're going to do product rule again, so we get to do it several times. So it's first one times derivative of the second. Derivative of the cosine is the negative sign, plus second derivative of the first. Moving on to the second term, first derivative of the second plus second derivative of the first. Moving on to the third term, first derivative of the second plus second derivative of the first. And then the last one, first one derivative of the second plus second derivative of the first. Now I'm going to see if anything cancels here. We have dx sine of x cancels. And we have e to x cosine of x cancels. So we are left with 2d e to the x cosine of x. When we put these together, minus 2 e times e to the x sine of x. And now we need to find a third derivative. And the reason we have to find a third derivative is we need a substitution in for that y triple prime. So product rule again. First derivative of the second plus second derivative of the first. And then first derivative of the second. Second derivative of the first. So now we can substitute everything into our differential equation. So we had y triple prime plus y double prime and that's equal to e to the x times cosine of x. So let's see if there's anything we can simplify. So I see I have 4d e to the x cosine of x. I have minus 4e times e to the x sine of x. And then it looks like minus 2d e to the x sine of x. Minus 2e e to the x cosine of x. And that's going to be equal to e to the x cosine of x. So we have e to the x cosine of x's and e to the x sine of x's. So let's build our system. We have 4d minus 2e has to be equal to 1, comparing those coefficients. And then for e to the x sine of x, we have minus 4e minus 2d, and I'm going to actually put that 2d first. And we don't have an e to the x sine of x on the right, so that coefficient is 0. We're going to use our calculator to solve the system. You could also do it by hand. using substitution or elimination. So I get the identity here for 2 by 2. I get 1/5 and negative 1/10. So that tells me that D is 1/5, E is negative 1/10. And if I substitute that back into our particular solution here, I would have y prime is equal to, or sorry, yp, which is particular, is equal to 1/5 e to the x sine of x minus 1/10 e to the x cosine of x. So then our general solution is the complementary plus the particular. Our complementary was C1 plus C2x plus C3 e to the negative x. Our particular is 1/5 e to the x times sine of x minus 1/10 e to the x cosine of x. Now, if we had initial conditions or boundary conditions, we would be able to solve for C1, C2, C3. Remember, this is a third order differential equation, which means you would need 3 conditions, whether they are initial or boundary, in order to solve for those 3 coefficients. So we can use the same technique not only on second order differential equations, but we can use it on higher order differential equations like third, fourth, and so on. It always works the same way. Find the solution to the associated homogeneous differential equation. Figure out what your particular is going to look like. Make sure there's no duplication between the complementary and the particular solution. Find your derivatives necessary to substitute into the differential equation. And then solve. And then form that general solution. And then once you form that general solution, if you have conditions, whether they are initial or boundary, you're going to sub those in to that general solution and solve for your C1, C2 if it's second order, C3 if it's third order, and so on. That's all there is to it.